Hello, welcome to C++ Memory Safety in WebKit. I'm Jeff, I'm the WebKit architect at Apple. My background is that I'm a member of Apple's senior software technical staff, and I've been a WebKit contributor for just under 20 years. So I started at the JavaScript VM and kind of worked my way up from there. Before that, I studied computing in college and also semiotics, and psychoanalysis, and Shakespearean tragedies, and debate. And all 5 topics turn out to be equally relevant when a conversation turns to memory safety. So I'm really excited to talk to you today about how we're approaching memory safety in WebKit, not only because it's one of my rare opportunities to use all of my skills at the same time, but also because I think we have something valuable to share. So let's get started. If you maintain a large C++ codebase, then you may have heard that memory safety needs to wait for a big giant rewrite that's 10, 20, maybe 50 years down the road. Not CPP now, maybe CPP later, right? I think we've found a way to make incremental progress toward memory safety something that you can start right away. Hi, come on in. You may have heard that memory safety needs to be limited to a cherry-picked component that's carefully isolated from the rest of your project. I think we've found a way to make incremental progress toward memory safety something you can do throughout your project and even in your most complex code. And that's what I'm excited to talk about today. So let me introduce WebKit briefly, and then I'll explain why I think our experience can help you and why I think you can help us too. And then I'll spend most of this talk digging into the technical details of our approach and how it's working out so far. If you're not familiar, WebKit is the web browsing engine that powers Safari across all Apple products. It's also open source and cross-platform and used by other browsers and non-browsers on Apple OSs, Linux, Windows, other OSs. I'm told there's some WebKit code that runs on a blender. I've never blended anything with it. A modern browser engine is basically a portable operating system. So it's a lot of code, about 9 million lines of code, not counting libraries. And like many large cross-platform systems projects, WebKit is mostly written in C++. Among its other goals, WebKit has 2 essential goals: security and performance. This is why I think our experience might be interesting to you. Our experience addresses the nexus question that comes up when we talk about C++ and memory safety. Can I have memory safety and still performance? Can I have memory safety and still systems programming? Or as I like to say, like, if C++ were memory safe, would it even recognize itself in the mirror? Right? I use the spaceship operator. I know C++. Meanwhile, we've tested our answers in the harshest environment I can imagine, the internet. If we make a security mistake, if I make a security mistake, there are dedicated nation state and criminal organizations that let me know pretty quickly. And if I make a performance mistake, there are dedicated competing browsers with huge marketing budgets that let me know pretty quickly. I think some of those budgets may be represented in the room today. That's okay. We can collaborate. So I like to say that we've assembled the largest volunteer QA organization in the history of software. And we've done a speed run through most of the security and performance issues you're likely to encounter in a project. And the solutions that have held up in our environment are likely to hold up in yours too. That's my hope. So my agenda today is to examine our approach, to show you what's possible and what's working for us, and also its limitations. And then I'm hoping if you're a project maintainer interested in memory safety, you'll see some techniques that might work for you or be inspired to invent your own, similar to our approach. And if you're a compiler author or a standards participant, I'm really hoping you'll consider the ways that you can support our work as you evolve the compilers and the standards, because we need your support. the more solutions we can build into de facto standards in our compilers, where the compilers mostly agree with each other, or the de jure standard in ISO C++, the easier this all becomes for everyone. So let's dig into the technical details. So before we define our solution, let's make sure to define our problem. We define a memory safety bug to be a bug that can create a weird machine. On a modern OS, an attacker can't change the running program since the running program resides in read-only memory and is also cryptographically signed. And so instead, the attacker damages the underlying abstract machine that's running the program by writing to non-program memory locations that influence execution state. The net result is as if the attacker had changed the program, so they can take over the program. Weird machine bugs are Turing complete, so even one weird machine bug is a sufficient gadget to reprogram an entire process. So that's why these bugs are so important to us. They're the most powerful primitives available to an attacker today. We use the word can intentionally in our definition of a memory safety bug. We treat all bugs that can create a weird machine as if they do, without requiring a full demonstration. We have enough experience by now to know that in a hostile environment, any bug that can create a weird machine eventually will be used. We address memory using pointers, so memory safety bugs are fundamentally pointer bugs. Every pointer has a lifetime, a certain duration in which you can use the memory it points to. If you use the memory before or after that, you can write to memory that you shouldn't. Every pointer has a bounds, a beginning and an end. And if you use memory prior to the beginning or past the end, you can write to memory you shouldn't. And every pointer has a type, which is a way to interpret the bits in memory. And if you interpret them incorrectly, you can write to memory that you shouldn't. And then there's this bonus category of undefined behavior, where C++ reserves for itself the right to create memory safety bugs whole cloth, even if they were never originally expressed in your source code. We need to tackle that too. Notice that null pointer is only in our taxonomy because of undefined behavior. If a null pointer dereference happens at runtime, that's guaranteed to be a trap on all modern OSs, and all our security experts agree there's no security impact whatsoever. It is if and only if the compiler notices the null pointer, and only because C++ says that's undefined behavior that we then have a memory safety problem. There are about 175 other cases in the standard. So if memory safety means a bug that can create a weird machine, then if memory unsafety means a bug that can create a weird machine, memory safety must mean like not having any of those bugs. Honestly, that's the goal, right? We're a project that has memory safety bugs. We want them to go away. Cool. Done. This definition says what we want. It doesn't say what we do, right? We're an engineering project. We do things. And so we need a definition that says what we do. And so what we do is rule out various classes of memory safety bugs incrementally and at compile time. And these two features are really important. Incrementally means that we evaluate memory safety one body of text at a time and one safety property at a time, and then we compose the results. And that's important because it breaks down an enormous project into achievable pieces, so we can measure improvement and prevent backsliding. That's instead of sort of creating a rigid barrier between safe code and unsafe code so that we can weave safety into all of our code. At compile time means that we're using tools to enforce a safer C++ dialect. And we're automatically rejecting any code that doesn't conform. So our thesis is if it's not safe, it shouldn't compile. And that's important because it clearly communicates what we're asking programmers to do. And it gets us out of the business of evaluating memory safety in our heads, which we know doesn't work. So now that we've defined what we're going to do, how do we do it in practice, right? And so let's go in order from some simple cases to more complex, and I'll show you the specifics, and I'll start with bounds. Okay? So here's a memory safety bug we had with bounds. Sorry, you can't exploit it anymore. It's been fixed. Fixes shipped to customers. We're trying to blur a few pixels at the edge of a layer, okay? And we're using a lot of cursors and offsets and conditionals and arithmetic to compute how the different pixels are going to influence each other. And somewhere in there, if given a very specific pixel and blur combination, we write past the end of the buffer. Oops. So this is a pretty good example of why we need memory safety. The full function is like 2 screenfuls long. There's just no way that any human can tell you whether that function is going to index out of bounds or not for all inputs. It's also an example of why we need to kind of weave safety into all of our code. It's tempting to believe that memory safety bugs only happen in new code, right? I tracked this code back 15 years before I ran out of Git skills because there were too many repository migrations and file rename. This is old code. So luckily, Clang offers this handy warning called unsafe buffer usage. So using this warning and treating warnings as errors, we enforce a dialect in which we rule out out-of-bounds access. The warning is quite stupid in the best way possible, in the sense of keep it simple, stupid. It's entirely based on syntax, okay? There's no data flow. The compiler doesn't try to reason about which pointers have which bounds or whether an index ends up in bounds. It just warns about any expression that does pointer arithmetic. That's why you see the carets under the plus equals. That's the pointer arithmetic, right? So you'll see that focusing on syntax and not data flow is a theme in our safer C++ dialect. Data flow analysis about program correctness is capital H hard because of pointer aliasing. Very quickly, if you're being specific in your analysis, it says anything is possible and you accomplish nothing. But syntactic analysis, pretty straightforward. You just look at the tokens in the abstract syntax tree and you know what's what. They kind of tell you a lot. And it's also straightforward to communicate the rules to programmers, right? Pointer arithmetic, straight to jail. Indexing into a buffer, surprise, also jail, right? So the fix is to enable Clang's standard library hardening mode and adopt standard span. Once you change that input declaration to span and propagate that through the rest of the function, it's bound safe. And any out-of-bounds access will trap at runtime. Other buffer types work too. You can use standard array, you can use standard vector, it's fine. Okay. What about this bound safety bug we had? So is it clear why the old strategy doesn't work here? The actual pointer arithmetic is inside the library function. And so our compiler doesn't see it. If you haven't seen it, Google Project Zero did a write-up on this bug. It's high quality. If you want to learn how exploits work in detail, and you don't mind people saying slightly mean things about my work, I invite you to read it. Here we're copying an IPC buffer into a metal GPU texture, but the crafty IPC source has sent us too many bytes. Okay? So it turns out there aren't all that many library functions that do unbounds check memory copies. And so it's practical to annotate the functions as unsafe, and libc and libc++ do this now in Clang, and so Clang warns about them too. Okay? You can think about this as sort of similar, I suppose, to the unsafe trait in Rust. It's your obligation to put it there now. So at API boundaries, where the other side of the boundary doesn't use span, we write helper functions to encapsulate unsafety. Okay? So the moment a pointer flows into our code, we start enforcing its bounds right away. That's what the unsafe makespan helper function is for. And right before a pointer flows out of our code, we check its bounds. That's what memcopy_span does in the case of memcopy. And then inside memcopy_span, release assert is our macro for trapping at runtime, even in release builds. The allow unsafe buffer usage macro expands to a pragma that ignores the warning. And the social expectation is that at the boundary where you use that macro, you're doing the bounds check. So here are all the pieces you need to put together to establish this dialect for bound safety. A compiler warning for pointer arithmetic, treating warnings as errors, bound safe standard library containers, and a way to turn off checking as needed at those API boundaries. When we started, we turned on bound safety enforcement globally in our build system, and then we used our allow macros to skip all the files that didn't conform. And then over time, we just burned down one file at a time, remove the macro, fix the errors, everybody happy. So after a year of work, 94% of WebKit, as counted by source file, conforms to our dialect for safe bounds. That's a lot faster than 50 years. And it's a lot more code coverage than a cherry-picked component with purity of essence in that component. Now the controversial bit. The measured performance cost is 0. And this is going to be a theme today. Let me foreshadow that. We have a policy in WebKit. You can't check in a patch that regresses performance. So if it's in the tree, it must have been measured not to regress performance. So performance in this case is defined as end-to-end performance as measured by a variety of competitive benchmarks that are accurate to the tens of microseconds. So I've learned that for a lot of you, that's pretty accurate, and for some of you, it's not even a start at accuracy. We measure using A/B tests for patch-to-patch changes. For this change, we've also measured the end-to-end result of enabling and disabling the hardened standard library altogether, which I admit happened by accident. And when we turned it back on, we measured. So adding an extra loading branch isn't always free. We did have a handful of patches, maybe like 2 to 4, that A/B tested as less than 1% regressions. And then we needed to rework them before landing. So I think this is a feasible way to program for most projects these days. And I don't know, to me, it still looks like C++ and systems programming. So if you're a project maintainer, I'd invite you to try it out, right? Why not? And if you're a compiler or a standard library author, I'd invite you to think through the ways the compiler and the standard library can help us with this, the ways we can evolve a de facto standard through shared warnings, shared flags for turning on a hardened standard library, and then ultimately something we can specify if you want to program ruling out bound safety bugs, which I think a lot of people do already and more will as time goes on. Any questions about bounds? All right, cool, solved. Go ahead. Yeah.
That only applies if you use Clang, right?
We're using Clang, and the specific syntax I showed is Clang syntax. So that's sort of part of my sales pitch here, I guess. What would it look like to support this in MSVC and GCC? I think we need some more of that.
Yeah.
Anything else? Okay, let's move on to type. So here's a memory safety bug we had from a bad pointer cast. Okay. We represent scrolling using a tree of nodes. The programmer is pretty sure here they're scrolling an HTML frame element. And so they downcast to that node type, but they're mistaken. It's possible for something else to be scrolled in this case. And so now they're addressing additional fields in the object and additional function pointers in the vtable that aren't actually there. Okay, oops. So here's our preferred fix. Instead of static cast, we use downcast, a custom helper function that does a runtime type check, and it traps if it fails. So because downcast is a function template, it's super duper flexible, right? Anybody can write any description of how to check a type, and whether it's a virtual function call or a load from a bit field, or you can even call into a foreign language runtime, and then it all just plugs right into the template. So we noticed a condition that can create memory unsafety. We developed an idiom that rules it out. Now we want everyone to program that way. How do we do that? Right? Normally, that's what a programming language is for, right? Unfortunately, ISO C++ doesn't help us with this yet. And even Clang doesn't offer a warning for this yet either. So what we turn to instead is static analysis. So we wrote a custom static analysis that bans all non-trivial pointer casts. Non-trivial pointer cast, straight to jail. And here's an example of what it looks like when it reports that the analysis has caught something. This doesn't mean that the cast is incorrect. It means that we don't know if it's correct or not. Okay? So we built our analysis using the Clang static analyzer, libanalysis, which is just an interface to Clang's AST and some, and not just, it has a bunch of other great stuff in there, but that's the kind of premise of it. And like unsafe buffer usage, it's entirely an analysis based on syntax. And then we enforce this analysis in continuous integration, not at desk. And that's a limitation to our approach. We'd love to give people direct feedback at desk. But because this analysis is not built into Clang, you have to build a second time to get the analysis. And we want to amortize that cost by waiting until you're ready for your patch to be reviewed. And then finally, we make enforcement incremental using a per file allow list and per line skip lists if you need them, skip annotations if you need them, using the existing Clang libanalysis syntax for skipping an expression. Okay, so sometimes our dialect requires us to change code that's already safe, right? It really depends on whether your definition of safety is what we're going to do or what we're hoping the result is. If it's what we're going to do, this code is actually not safe because it doesn't demonstrate its safety at compile time. So this is an example patch motivated by the analysis. This is code that uses the BSD sockets API. And if you had data flow analysis and you had an understanding of the socket type, you would know that AF_INET means IPv4 address. And you would know that this cast was already safe to begin with. But our analysis doesn't know those things, and so our code had to change. Right? So now it looks different from before, but like in my view, like we're still programming with BSD sockets. This is like systems programming, right? It's cool. We're cool. We're still C++ here. After a year of work, 98% of WebKit is conforms to our dialect for enforcing casting safety. That's a lot, right? I was surprised by this, right? In the beginning of the project, I very carefully picked the most valuable 100,000 lines of code and said, all right, this is our goal. And then we met that goal in a month. And then I was like, okay, I'll write static analysis to find all the reachable code from that 100,000 lines. And I picked like 400,000 more. By the time the analysis was done, the code had already been covered. And it just like caught on in the project like wildfire. And then I stopped writing analysis to find more code and just accepted that we're going to cover all the code. It's inevitable, right? Yeah.
So this is fantastic. Did you have a centralized push, or this is just like word of mouth? Like, how did you get developers to kind of jump?
Oh my God, let me tell you a story. We work with this guy. He's great. He's been at Apple since God was a child. He's earned some Emmys, and he's half retired now. So he's working half-time. He goes to his apple farm for a week at a time, and then he comes back and he works a week at a time. So he's at his apple farm, right? And then we turn on one of these analyses for the first time while he's picking apples. He shows up Monday morning, and he's got a patch for safer C++. And I'm like, who told you? I don't know. I think there's just an enormous amount of pent-up demand and a lot of monkey see, monkey do, and it just, right? Yeah.
So did you actually also try a Clang tidy check instead of your own plugin?
Which one did you have in mind?
I'm just saying that you could write your own Clang tidy check.
Oh, right. We didn't do that, and I don't know why. The engineers talked, they decided to build it this way. I think it's because we like this output better, but I'm not sure. And maybe we still could. There's not a lot of difference, right? It's all AST based. Maybe someday it'll make it into Clang tidy. I think it's a good suggestion. But I don't think, like, if you're thinking Clang tidy, I'm not aware of any fundamental barrier there. Okay, so, also like zero performance cost as measured in our project. And in this one, there was never even a patch-to-patch A/B test that complained. These checks, they seem to be pretty cheap. So I think it's a feasible way to program. I know this isn't how a lot of C++ code is written yet today, but it still looks like C++ to me. It's very flexible with a template, and try it out. Like, nothing stops you from just trying it in one file and then another, and suddenly you're just doing it, right? And for for compiler authors and standards participants, again, it would help us so much if we had a shared view across different compilers of like, is there a warning I can turn on for like W unsafe pointer cast, and does it need to be split into multiple warnings? And then ultimately, is there a way in the language to convey, I understand this is a language that's capable of lots of casts, but please let me know if they're happening here and don't allow them, right? And let's create a taxonomy for what's allowed and not allowed, right? I think that would be really valuable. If you zoom way out, something else to consider is that tools like this static analysis are inevitable, okay? Either we write these tools that rule out bugs in the first place, or attackers write these tools that find our bugs after the fact. And so long as humanity is going to invest all of its brain power into building these tools, let's just build them for us. Why not, right? Okay, now let's do something hard. Everyone take a break. Shuffle off your disbelief. We're going to talk about object lifetime in C++. So I want to start with reference counted objects because in our project, that's where we typically have the biggest problem. And I would speculate the reason why is by the time you're reference counting the object, that's your indication that you don't know what its lifetime is going to be. And so that's your invitation to make mistakes. So like a lot of projects, WebKit defines a few custom classes for reference counting. RefCounted is a base class that adds the counter to your object, and CanMakeWeakPointer adds support for nullable weak pointers. And then RefPointer is a smart pointer that holds a strong reference, and WeakPointer is a smart pointer that holds a weak reference. And we have other smart pointer types that deal with different object types, but they work the same way. So is that kind of clear? Once an object conforms to RefCounted, you can make a ref pointer. When it conforms to CanMakeWeakPointer, you can make a weak pointer. What a name. Isn't that an awesome name? Okay, so here's a memory safety bug we had from a missing reference count. RTC peer connection is reference counted, and RTC ice transport holds a weak pointer to it. Okay? Inside on state changed, the arrow operator passes mConnection as a raw pointer to process ice transport state changed, right? The implicit this parameter, it's just a raw pointer. So weak pointer is single threaded, so it's a valid optimization that the arrow operator is returning a raw pointer to us, and we need it, in this context, we sort of need it to anyway, because in C++ you can't mess with this, it's always a pointer. So the problem is we never declare a local ref pointer, so we have no local reference count to this object. And inside process ice transport state changed, anything can drop its reference count. The reference count can hit 0, and then we end up with use after free. Oops. So here's our preferred fix. To guarantee the lifetime of mConnection, we need to declare a local ref pointer. Okay. So now we want everyone to program this way. How do we do that?
Write an analysis.
Right. ISO C++ and Clang don't help us with this. So again, for this, we did static analysis. So here's an example of our analysis reporting that it can't guarantee the lifetime of audio context across a call to the destination function. The analysis is still based on syntax, but it's more complex than the last. What it's saying is that any use of a pointer to a reference counted type requires a reference counting smart pointer to be declared in an overlooking scope. So let me show you that. And I'll break down these examples of the overlooking scope rule top to bottom. So object is an example of a reference counted object. It inherits from ref counted. Use and use inline are examples of functions that use an object pointer. Okay? Inside the object class, raw member is an error because it has no overlooking scope, right? You can't give a scope to a heap data member, and so all raw pointer data members to reference counted objects are errors in this dialect. Inside the use pointers member function, use argument is okay because analysis must have proved that our caller has a ref pointer to argument. Use const_member.get is okay because this is implicitly in scope, just like arguments. So our caller must have a ref pointer to this. Const member is a part of this and can't change. And so const cast in our system is an unsafe cast. Use ref pointer member.get is okay because we have a local smart pointer on the stack in that case. Use member.get is an error. In that case, even though this is in scope, member can be reassigned. We have no overlooking scope of a ref pointer. Use inline member.get is really interesting. That's allowed, even though use was not allowed. I know. Crinkle your brow. Why is this allowed? What magic? So we're not guaranteeing member's lifetime, and the analysis knows it. Okay? But the analysis sees that use inline is inline, right? And it sees the AST for the function, and it sees that it's a trivial function. It doesn't contain any expressions that can delete, okay? And it can truly see. It can see the way C++ can see. Even if there are overloaded operators, doesn't matter. I look at everything. If anything's not present, I don't know. If everything is present, I have an allow list of expressions, and we're cool. So this turned out to be really, really valuable for us. Not for performance, but just for our fingers. Like, there are so many ref pointers you have to type if you don't have this analysis, and they all just disappear because your tiny inline getter functions, they don't matter to analysis anymore. This is something we kind of discovered by doing this work. And then finally at the bottom, use get object is an error because we don't know where the return pointer came from, so we have to assume the worst. Any questions about the overlooking scope rule?
Could we go back to the slide before and just see where the error was again?
Sorry if it's small. Yeah, so we're going to call the destination function, but it's out of line. We don't know what's going to happen in there, so we need an overlooking ref pointer on the stack. But we don't have one. We have a raw pointer. And so the analysis sees that and says, sorry. There's one other fancy thing this analysis can do. This is a slightly fancier case. Using a raw pointer derived from a ref pointer is also okay. The raw pointer is fine, even in the presence of control flow. But if you do, we then prohibit reassignment of that ref pointer. So you didn't have to mark it const. We just know, did you assign or not? Did you take its address, pass its address to someone or not? So anytime you get an error, you can always cure it by declaring a new smart pointer. Or if you prefer, you can inline a trivial function and get a lot of call sites not to have to care anymore. So this isn't a novel scheme. Reference counting is not new. And if you're familiar with systems like automatic reference counting in Objective-C and Swift, or the RC type in Rust, they have similar rules. What's novel here slightly is reasoning in terms that C++ can currently express using smart pointers in scope, and then enforcing it with static analysis. So we're a year in, and we're at 90%. 90% of WebKit conforms to our dialect for smart pointers. So it's a bit slower than the others, but I think this still says it's practical. And then again, 0 measured end-to-end performance cost. So as with bounds checks, adding reference counts isn't always free, and we did have a couple of patches that needed to be reworked along the way. And we also take liberal advantage of single-threaded reference counting where it's appropriate, and depending on your platform, they may have different performance. Yeah.
So how do you measure a performance impact? Is that like, so every time, someone changes a small piece of code to conform to that idiom, right? Then you measure just that, or do you have somehow a way to measure the global impact of the whole change?
Yeah, so we're measuring each patch with A/B testing, and so typically someone will say, "Oh, I took this folder, I got it to conform. Here's my patch," right? With bounds safety, we are able to also measure globally because you can just turn on and off the enforcement inside standard span, which is most of the enforcement we use, but not all. For reference counting, there's no way to just turn off all the reference counts, so I don't have a global measure, right? Go ahead.
But if I understand correctly, you do it patch by patch.
That's right.
So if the measurement measures a lot of things, the small change may disappear into the noise, right? So I don't know whether it's viable or possible to measure sort of before all of the or a substantial amount of patches have come in, and after and see whether there's a patch.
We are able to measure that too, and that also shows no regression.
Okay.
The additional variable that creates noise in that environment is what if someone else checked in a speed up too, right? So we may be, if you just measure like January to May, you may be not noticing the fact that your safety work, spent some of your speed ups,
Okay.
and then the hope is that the per patch measurement is catching that as much as possible within the resolving power of the benchmarks, such as they are. Given the overall result, I think this is a feasible way to program most of the time, right? Just reference count your object. What might it look like in your project to just take like one type at a time and say, oh, I'm going to reference count this. It's cool. And then in the beginning, maybe you enforce an overlapping scope rule somewhat manually. Maybe it's not perfect like a tool would be, right? I don't have a product to offer you for this yet. Our WebKit checker right now is pretty WebKit specific, but the logic is not. And so could you program this way? Yeah, go ahead.
A different question I have actually on all of these guys is, do you have a measure of how many bugs that detected? I realize that it is tricky, but for example, for the reference count, one could, in theory, actually use the annotated reference count when you capture that new, and assert for a report that the reference count would have gone to 0.
Yeah. So Well, so are you wondering like how many historical bugs are ruled out by this mechanism, or?
I mean, let's say you the overlooking ref count. Now you have it, means the thing doesn't get released potentially. But in the past, without that thing, there may have been bugs where it did get released, which are not discovered yet. Right? But basically by doing that and then possibly asserting that, oh, right, it would have gone to 0, you could actually discover this actually detected the bug or prevented the bug which was dormant.
So, we have a version of that where like we run fuzzers and then we can detect the cases the fuzzers have found and then whether they've been resolved. The challenge here, though, and the fundamental challenge of memory safety in an internet connected environment is the set of all things that our fuzzers just don't reach right now, right? And the fear of a latent thing, if you're not ruling out a compile time, you just never know, right?
I understand, right? But one of the things, if I go to my management and say, oh, this is a cool idea, we should do it, they will invariably ask me, is that just something you want to do? And it doesn't address anything. But if you had told me, all right, we spent that amount of time, but we also found that amount of bugs.
Well, here's something I can tell your management then. If you do a historical classification of the memory safety bugs we've had in WebKit, and you have to classify by hand, which is a little fraught because every memory safety bug can cause every other memory safety bug. But if you take that classification as a premise, roughly 95 to 99% of the memory safety bugs we've ever experienced in WebKit are fully ruled out by these rules once they're applied. So that's not a promise that no new bugs, no new styles of bugs. That's explicitly not a promise that nothing will be found in the future. But attacking what we have now is really valuable to us. Yeah.
Yeah, I want to say that even management often understands that confidence has a value of its own. And if you can say confidently that these bugs aren't happening, that's valuable.
Yeah, I think that's a really good point. And another way to frame it is, well, if somebody's got a fuzzer that's looking for our out-of-bounds accesses, they have to throw it in the garbage. They have to make a new fuzzer to look for something else, right? So, we could use a lot of help, I think, from compilers and ISO C++ again on, like, what would it look like to have a shared description for, I need an overlooking something in this scope? Can it be like a W, no overlooking ref count? Can there be a C++ profile that says there are certain types that declare they conform, and then there has to be something in context to demonstrate the conformance? I think it could be really helpful.
You said the magic word profile. You must be aware of the profiles work going on in the committee.
I've heard of it. I don't know the current state.
It has some current state, but it is in the direction you are looking for.
That would be really helpful.
Sorry.
Oh, okay. Sorry.
Oh, I will say I do know one thing about the current state, which is it's not going to land in 26.
Okay. Yeah. Okay, so what about objects that aren't reference counted, right? If you have a reference counted object, the beauty of it is you can always extend its lifetime. Very simple thing to express. What about something whose lifetime you just can't extend, right? There's an object that has a semaphore inside. That's an address. And it's not reference counted, but you need to use it for a while, right? So here's an example that happened in WebKit. To my surprise, our most common lifetime issues, once the ref counted issues are resolved, are these relatively trivial cases of dangling view types. So a view type is a type whose job is to point into another object, doesn't own the object. If you copy the view, you have no ownership of what you've copied. And so here's an example where the programmer was trying to get the host from a URL. Pretty simple thing to do. Shouldn't require multiple security experts to comment on. So the problem here is UTF-8 returns a string temporary because it may have to do an encoding conversion. And then data returns a string view, a view into that temporary, and then the temporary goes out of scope. So this is immediate use after free caused by a dangling view into an unowned temporary. So here's a similar case we had with a string builder. The string builder is locally allocated on the stack. And so the return is a use after free. It's a dangling view into that builder that was on the stack. So luckily, Clang offers this handy attribute called lifetime bound, right? And lifetime bound means that the lifetime of the return value depends on the lifetime of this. So it's a way to chain lifetime back to its source.
So this wouldn't work for the last example, but the first example, one thing you could have done, maybe delete, overload these pointers like a nar value reference, right? Mm-hmm. So like you're not allowed to call that on a temporary, right?
Not allowed to call the string view constructor on a temporary?
Yes, or the data member function. You could delete that for just, temporaries, right? By deleting.
Oh, that's a cool idea.
Yeah, overload. Yeah.
Okay.
I think that there are times when it's okay if you're passing a state to a function and then it's used within a function and then it goes away. So it's only because it escapes the expression.
That's true. Yeah.
You have to reason about like the lifetime would be extended or not. Like if you're doing that on the call.
Okay. Yeah. So there are some options there. Yeah, but I think lifetime bound is a bit stronger, or at least a bit more universal. So we're just chaining lifetime back to its source. Yeah.
One quick question. So since you mentioned that you're using libc++ in the hardened mode, see if the string view actually is dangling, when you try to access it, won't it just crash without an exploit?
I don't know for the standard library. This class is the WebKit string view class, which behaves a little differently, but it's still a view type. And then WebKit string class is not the standard string class. And so that, but yeah, maybe in another project that's using standard string and standard string view, maybe hardening is enough. I'm not sure if it is.
But yeah, I'm now thinking out loud. It's not possible because it cannot look at the data pointer. So.
Okay. Yeah. Okay. Okay. So we chain the ownership back to its source. So here's the error you get once you've adopted this attribute. Once Clang knows which lifetime depends on which other, it will alert you when B depends on A and the scope of B exceeds the scope of A. And so here again, we're relying on syntax and scope and not on data flow primarily. So here are all the pieces required to establish this dialect for non-reference counted lifetime safety. A compiler warning for dangling references, which is on by default in Clang, treating warnings as errors to give it teeth. And then you need to hand apply lifetime bound to APIs that return view types. Okay? So this part of our dialect is a work in progress. We've done enough adoption to know it's catching the most important bugs. But we have significant gaps relative to our goal of automatic compile time enforcement. One, Clang doesn't know which APIs need lifetime bound, right? So the most important future direction, in my view, is how to warn when the lifetime dependency is dropped or when it's just unknown. 2, Dangling is shy in its current implementation. It will only tell you if it can definitively prove you're doing use after free. If it's just not sure, it doesn't say anything. And so a significant future direction is to beef that up. And 3, Dangling guards against destruction only, not mutation. Okay? So if I have a view into an object that can change, right? Like my string view is into a string builder. If I append more to the string builder, it might internally reallocate and free the old buffer. You need a way to trap if that object mutates in a way that violates your view type. And our plan for that is a smart pointer, but we haven't done that yet. So I can't give you an adoption percentage for this one because we don't have analysis yet that would tell us. That's part of our future direction. I can give you the performance number is 0. This is all compile time. This is true 0. Right? So I don't know. It's still pretty C++y, right? All I do is I return the same pointers and references I used to. I just give the compiler a little more information about where they came from. And then it helps me reason about like whatever level of enforcement I want for how much information needs to be there. Ooh, fun. Okay, let's move on to undefined behavior. So undefined behavior I call the friendly neighborhood ghost. It haunts all C++ code and all our safety techniques at C++. Nearly every feature of C++ admits undefined behavior. About 175 citations of the phrase exist in ISO C++. And undefined behavior doesn't just mean that the compiler can't promise a specific outcome. It also means that the compiler is invited when it can promise a specific outcome to guarantee the worst possible outcome. Right? So when we write a bounds check like this one from our memcopy span function, it always comes with this implicit ghost that means the compiler might emit this bounds check, or if it has detected undefined behavior anywhere else in your program, it might just not. Okay? And so I said our bounds checking adoption rate is 94%. Actually, it's a statistical distribution that's between 94% and 0%, depending on how spooky the compiler is feeling today. Right? Now, in practice, the distribution is usually pretty close to 94%. That's why I call it a friendly ghost. Right? But it's a big problem that it's not actually 94% and that we can't know what the percentage actually is because we don't know which line of code the ghost will haunt next. So here's an example from WebKit where a programmer was trying to handle an out-of-bounds index. And I've radically simplified the original for clarity. The programmer was using standard span like we want. They did the thing they're supposed to do. We have the hardened C++ library. Everything's cool. The problem is, in a sufficiently complex situation, under certain circumstances, the programmer has messed up and they'll end up with a guaranteed infinite loop. Okay? Well, ISO C++ defines infinite loops to be undefined behavior. So the compiler's reasoning was the following. 1, if index is out of bounds, there's an infinite loop. 2, infinite loops are undefined behavior, so index was not out of bounds. 3, because index is not out of bounds, I can delete the bounds check inside the if condition and also the bounds check inside the span bracket operator. This is a clever compiler for a clever language. Go ahead.
I mean, even if it weren't for the undefined behavior, the return statement would be unreachable in that case. So
that's right. So it would, in a certain alternative universe, it would have been a hang. We don't like hangs, but we like them a lot more than somebody breaking into your computer. It was definitely a bug, right? If you think back to that original graphic, we don't make all the bugs go away. We just make the weird machine part. That's the goal. We make that go away. So here, if and only if the compiler can prove that an index is out of bounds, it will remove the bounds check and cause an out of bounds access.
Oh, I could add that we are adding a mitigation for this in C++ 26. That's actually made it into the draft.
Fantastic.
And it is only a mitigation against future undefined behavior in affecting the current thing, not the other way around. Past undefined behavior is your problem.
Okay.
But
So it's a mitigation against time travel, basically?
Yes,
Okay.
the backward time travel that you get from undefined behavior, you can mitigate that, and it's built into contracts that assertions can't be, do have this mitigation built in.
That's great. That's really great. That's really helpful.
If you look for Davis
Herring.
yeah, I don't remember the name of the title or the number of the paper, but it was written by Davis Herring.
Thank
And
you.
it's
That's really great.
Really,
And that's sort of part of my thinking here is like anything helps, right? And everything helps. Okay, that's. Let me just do one more. Oh, go ahead.
When you say anything helps, there's something which is important for standardization, and that is somebody who wants something should propose it. Because relying on the others to propose it,
Yeah.
they may not be aware that they want it, and they may be busy proposing the stuff they want. So I accept that the standard committee is not doing what you want, but if you want them to do it, propose it.
That's fair feedback. Yeah.
I will say,
And they are doing some things,
I wanted the
right?
thing that Davis did for a long time, but I didn't think it was possible.
Yeah. Yeah.
And he showed it was possible.
Cool.
That's some of that.
So we'll do one more. Here's this is real. This is an example where a programmer was trying to show a password UI. Again, I've had to radically simplify the original for clarity, but this is real. So the programmer is using ref pointer and weak pointer like we want. They're managing reference counted lifetime like we want. The problem is, along this code path, the compiler was able to inline some code inside should show password popup and prove that along this path, that code will always delete the password popup object and store null to the password popup weak pointer like it should. But ISO C++ defines dereferencing the null pointer to be undefined behavior. So the compiler's reasoning was the following. 1, the ref pointer initialization loads from null pointer. 2, load from null pointer is undefined. So the store of null pointer must never have happened. 3, now I can reuse the deleted pointer I still have in a register because nobody's ever overwritten it. And so if and only if the compiler can prove the password popup has been freed, then it will turn your weak pointer into a raw pointer and cause a use after free. Oops. So I could go on, but my security colleagues at Apple have asked me not to. I hope you'll take my word for it, given the examples I have provided, that even though bugs like this are not super common, they definitely happen and we need to address them. They're common enough that we need to address them. So for the foreseeable future, we will be maintaining a large C++ code base. And that means we will be iteratively identifying our top remaining memory unsafeties, building static analyses that rule them out. And I welcome efforts by compiler authors to help by adding warnings that make plain the cases where the compiler is certain there's undefined behavior, and also flags to constrain undefined behavior even if we can't fully control it. And I welcome efforts by ISO C++ to eliminate unnecessary undefined behaviors like time travel or like maybe we can do infinite loops next. And I recognize my own responsibility to propose some things too. Or another thing to consider is transitioning to unspecified or vendor-specified behavior, where maybe the standard doesn't guarantee what will happen, but it also isn't carte blanche to do nonsense. Go ahead.
Something did happen with infinite loops at the last standards meeting. I don't know the details.
Okay. Great. It helps. So in this context, how do we finish the job, right? How do we get a body of text out of this system and make sure it's not haunted by the ghost of undefined behavior and enforce our memory safety idioms without exception, right? That's the question my bosses ask me, right? So it turns out there is something that's in our power to do, and that's adopting a memory-safe language. So WebKit is adopting Swift as a memory-safe language, and our C for C++ dialect not only provides immediate benefits for incremental improvements in safety, it also provides a mechanism to interoperate with Swift in a memory-safe manner. And that's really important to us. We think of a memory-safe language as a yes and, not an either or. Okay? As I like to say, don't hate, interoperate. Okay? We do not treat memory safety and memory unsafety as isolated worlds with alien concepts. We invent one shared concept for how the data works, and then we apply that concept across languages. And with strict memory safety checking enabled and warnings treated as errors, Swift will enforce that concept without exception. So you may have seen John McCall's 2023 CPP Now talk, where he acknowledged that a little bit of unsafety might be inevitable at the interface between Swift and C++, and now with strict memory safety checking enabled and warnings treated as errors, we've removed that loophole. And I think that's a really neat development. So here's a summary of all the concepts we've covered today, and we use the same concept in C++ and in Swift. Sometimes C++ syntax doesn't fully express the facts that are required to choose the right concept. And so in those cases, we add the facts as source code annotations. And the main missing facts are typically about object lifetime. Okay? So when an object is reference counted, the Swift shared reference annotation tells the compiler that it is reference counted, and it tells it which C++ function to call in order to increment and decrement the ref count. The Swift non-escapable annotation tells the compiler that a type is not reference counted, and then that requires Clang lifetime bound to state its lifetime dependency wherever you're using it. And then there are a few others I'm not going to cover today. So crucially, we don't tell the compiler what to do. We tell the compiler what we know. And then we ask it to reason about what to do. And with strict memory safety checking enabled and warnings treated as errors, if there are any missing facts or contradictory facts, then we get an error. So once one engineer has paid the one-time cost to annotate an interface with its meaning, and it's with its missing facts, and then from then on, all engineers can use that interface from Swift without doing that work again. So strict memory safety checking and its interface to C++ are hot off the presses in open source. They are so hot that they may burn your fingers if you touch them right now. So we're just getting started adopting them in WebKit, but I want to show you a couple examples to give you a flavor of how they work. So here's an example from our work in WebGPU, which is a 3D graphics API. Texture is a reference counted C++ class, and it wraps MTL texture, which is a reference counted Objective-C class. Okay, and we haven't talked about Objective-C today. It's a programming language. We use it. The Metal API is written with it. The key here is that Swift stitches together all that information, and so it gives us one local variable with an Objective-C reference count and one with a C++ reference count, and it's all done automatically. So with strict memory safety checking enabled, warnings treated as errors, if we're missing the Swift shared reference annotation, instead of getting an unsafe pointer now, we get an error. This is an unsafe type. So here's our string builder example from before. This is the thing we can already do in C++. We're just catching the same bug in a different syntax. But here's something new we can do in Swift. We also catch it if you forget the lifetime bound annotation. There's no exception. You have to have it. And then if you forget entirely to tell me that this is not an escapable type, and so I don't know if it's not escapable or reference counted, then it's just an unsafe type. That's still an error. Any questions about that? Okay, so a couple takeaways. I think incremental progress toward memory safety can start now and everywhere. You don't need anyone's permission. You can decide what's appropriate to your project, whether you want to start with bounds or cast safety or some reference counting or some view type enforcement. even if you don't have your own fancy static analysis, sometimes there are built-in warnings in your compiler. Sometimes you can just apply the idioms by hand at first, and then eventually you're in a better place once a tool becomes available to you. The end-to-end performance cost in WebKit has been zero. I cherish performance. I think it's great that people working on C++ are sticking to their guns about making sure that it's a language that can avoid overhead if you need it. But I think maybe we need to give a little attention to the fact that lots of techniques that can do a lot of good, they don't have a lot of measured overhead. And in our case, they have none. Undefined behavior haunts C++ a little bit. The more we can shave this down, the more we can trust our safety techniques. And you can help, and I can help. Whether you're working to maintain a project and spread the idiom in your project or maintain a compiler or the standard. And finally, I would say yes and if somebody brings up the topic of a memory safe language, right? When you do this work to codify memory safety, yes, it gives you enormous safety benefits right now. And it gives you the option, wherever you choose, to transition into a fully memory safe language, not by throwing away your code, not by erecting a wall around your code, but by fulfilling the concepts in your code without exception. Okay, thanks everybody.
Yeah, one quick question. So is WebKit the rendering engine of Safari?
Yeah.
So does these principles apply in Safari code also outside of the WebKit code?
Safari code is mostly written in Objective-C and increasingly in Swift. We do not have a plan to adopt safer C++ in Safari. And that's kind of an issue that's beneficial about our strategy specifically at Apple. Our global strategy of, hey, safer C++ is an option, integrating with Swift is an option. No matter how safe I make C++, lots of other engineers in Apple just don't program in it, right? So it's not a great solution for the whole platform, but it's a great helper in our specific context where we do use a lot of C++. Right? But I think the longer term strategy in Safari has been, we'll adopt like automatic reference counting in Objective-C as is, and then we can write some code in Swift and get memory safety that way. Yeah.
Can you explain more about the hardened mode of the library? I'm not familiar with that, and like if it is what I imagine it is, if it really had any performance impact that's noticeable.
So the hardened mode, my understanding is that right now, literally, it's bounce checks. Perhaps there's a idea of adding more safety in the future in other forms. But my understanding is that right now it's bounce checks, right? And so, I don't know. In our experience, what typically happens is, you switch to standard span, it's hardened, so now the bracket accessor has a bounce check in it, but you're already like inside a loop that's looping up to a bound, and so the compiler at the back end proves it away, and so there's no actual cost, right? And sometimes the compiler doesn't locally see it can prove away the bounds, but a modern consumer CPU, it just like chews up the instruction, right? Because it's mostly gated on the memory you're accessing, and a little bit of check on one of its like 16 parallel execution units will happen eventually. It'll be fine, right? But then there were a couple of cases where the compiler messed up its understanding of the bound of the loop, and so it stuck a bunch of bounce checks inside a really hot function, and we did have to like rework it to help the compiler and like file an LLVM bug for, why don't you understand standard min? Come on. If I'm looping to standard min of A and B, then all my bounds are less than B and less than A. Go ahead.
I'll throw in at the last meeting, the hardened standard library was approved for the draft of 26. And with first version, the way it looks in the standard is in the library section we can designate something, a precondition, as a hardened precondition, and that means if you are using the hardened, if you are compiling within the hardened library mode, then that will be then that precondition will be enforced at runtime, and it can be enforced through the contracts mechanism, but the standard doesn't actually specify the mechanism for enforcement.
But in this particular case, it only applies for bound read and write, right? It's not about lifetime of daily references. Or like string use.
It applies to whatever we say in the standard, but in fact, I don't remember every change where we put that in, but I think essentially every change where we have put that in so far is about the is about bounds checking.
I don't think they're lifetime ones.
Hmm?
I don't think they're lifetime
Yeah, I think
ones because you actually kind of cannot do it.
How did I talk to him?
I mean, but you cannot do it by basically saying, right, the system magically knows this value is still alive.
Yeah, you'd certainly have to specify some more things.
You need to.
Yeah. And then another interesting detail about the hardened mode is like, what about iterators, right? I spoke about indices. And it turns out there are two options. If you want an iterator to do bounds checking, you have to break ABI because it needs more information, right? So if you're in an environment where that's okay, maybe you're writing an OS kernel and you always recompile the whole kernel as one, then you just break the ABI and the iterators are considered safe, right? Because they have the new information, they're going to do the enforcement in hardened mode. In user space, at least on Apple OSs, we're not going to break the ABI. And so the iterators are considered unsafe. And so just like with memcopy, if you use one of the iterators, you'll get an unsafety error for the bounds check, from the bounds check warning. And one of the things that's been really interesting about that is it sort of forces you to program more with indices, right? Which is the inevitable result that's been seen in Swift and Rust as well, right? That iterators, it's hard to reason about their safety. Like if I'm trying to mutate with an iterator, but I also have an end iterator, that's immediately a conflict in a lot of systems of reasoning. And then, you also have to reason about their lifetime, whereas index is just an index, no reasoning, right? And so that's what we've ended up doing in WebKit because we're in user space. We can't use the hardened iterators, and so we just use indices everywhere. And it seems to work out okay. Yeah, and then...
So Chromium actually has this miracle PTR for handling lifetime kind of issues. Have you guys considered similar things for WebKit?
Yeah, so Miracle Pointer is a semi-reference counted pointer type that if the value is freed while someone's still pointing to it, it guarantees that either nothing will happen or you will trap, right? And then it's also the name of a script that will attempt to write patches against your code base to insert Miracle Pointer in all your data members, right? So one of our reference counting types does work this way. It's a way to say, I don't know if it's okay for me to keep this object alive, but I'm pretty sure it is alive, so just give me a trap if something bad happens. The big difference between the two approaches right now is that we're covering pointers on the stack too, right? I think at one point the Chromium project reported that they thought they'd fixed half of use after free bugs because they got the ones that were in the heap. But Miracle Pointer, at the analysis, it doesn't work on the stack. We want to get the other half, which is on the stack. So, it's great technology. I would say yes and to it. And we use a similar kind of pointer in some cases. But I think ultimately you want the pointers on the stack to be safe too.
Yeah, they may have made some updates to that, like which may handle stack also.
Okay, cool. Yeah.
So I already asked that question, but just want to hear more info. So you're based everything in Clang, right? In libc++.
Clang and libanalysis in Clang is most of it, yeah, and libc++.
And hardening mode is come from libc++, right?
Yes, although apparently it is also soon to be accepted to the standard and should be in
some way.
Yeah.
Sorry, I was just want to... Have you checked what the GCC does or MSCC does? Is there any similarities that it could be? Because Clang is the compiler lib to C++ there, but I think in my experience, majority using GCC or MSVC, not the Clang. So what to do in this type of projects?
I haven't checked in depth what MSVC and GCC are doing. And I guess this is part of the message of let's see if we can get our compilers onto the same page, offering at least similar warnings. Maybe they'll implement them differently. Maybe we'll finally standardize the specifics. But it sure sounds like, at least in the case of bounds, something has been standardized. So that's pretty great progress.
So on your move to a hardened lib C++, wasn't that already an ABI break for you?
It's not ABI break if you just add like bounds checks to like the bracket accessor. It doesn't change the shape of the object because the span always knew the pointer and the length. And anytime you make a new span, it's always a new pointer and a length. So you're cool.
Okay. I thought the C++ would like make different ABI for hardened mode just so that you could have like parts of the project linked with one library, a hardened one, other parts not. But I'm not sure like what's status of all that. That's why I'm asking.
Yeah, I don't think it'd be impossible to do that. It raises questions about, okay, if I have some part of my process running in hardened mode and some not, and then one piece of this code passes a span to the other, what happens, In our environment, we've decided not to raise that question, and there's just one ABI, and I wish we didn't have to write a couple of patches to like turn iterators into indices, but it's fine, it's fine. Yeah.
My question is more about WebKit as a whole. So it's been a couple years, but I tried to use Swift on Linux before, and I had a pretty hard time getting it to work. I just was curious, in the past few years, has Swift, adopted? Is it like available on more systems, like WebKit is?
There's been quite a bit of work for Swift portability. There's a package manager and a way to get a tool chain and so on. Of course, there's a big difference between portable software and software that has been ported, right? And I think that's a lot of the work we need to do this year is to make sure, to work directly with each non-Apple port participating in WebKit and like find out exactly what happens in anger when in that port, in that config, you set everything up and let the Rube Goldberg machine go. But it's a big priority for us, and it seems like a lot of the fundamentals are already there. There already are published Linux ports. There already are published Windows ports. There are tools for getting the toolchain and getting the standard library. We'll find out when we really do it in anger. And then there are some other ports that are a part of WebKit that might be interesting in this portability universe because, like, what about the Sony PlayStation? Right. But yeah, it's a high priority for us.
Maybe another question on how like you were saying that we spent a year to add the balance check, a year for like use up to 3. Did you enable the static analysis for the whole code base, and then like everyone who was changing suddenly need to change something, and if that happened that way, how all the developers felt about it? They were happy, or like, I don't know, say why I didn't touch anything, why should I do now?
So generally across all those technologies, the way we did it was the step one is like enable it for the whole project with appropriate skips. And so anybody who writes a new patch on day one, they get an error if they have not obeyed the dialect, right? And, in the beginning, there were some growing pains, all the growing pains you might expect. Like the bot itself had some bugs. The way it was reporting issues had some bugs. The analysis had some bugs, right? And there was some back and forth about, like, how does the model actually work? And that's what the trivial function analysis came out of, for example. Why, I know we need to obey rules, but this is so stupid. I'm calling a function that literally just says like return X, like, come on. And there was also been a process of like, well, what is the new idiom? Nobody's told me yet in this case. But generally, I think all the programmers on our project were hungry for this sort of thing, very supportive of it. And, you know, it's been going great. And I think you might find that. Like, I don't know what project you work on, but
I had an experience of enabling many like different specific wordings on compilers, and it was sometimes it was like some people like I feel like in your area people get tired of fighting these bugs, right, or fixing these issues, so they are happy. But in my experience, some developers who like doesn't really care about that, they kind of I used to do that way all the time, and I know my accessing and pointer arithmetic is good enough, and like they really against of any changes. And at some companies I used to work, we're just like, okay, our code base, this part will be guarded, this one we cannot do anything, they just don't want it.
yeah.
And they need to deal with that kind of by themselves.
Yeah,
That's
this
why
is
I'm
where the psychoanalysis and Shakespearean
Yeah.
tragedy become useful.
Yes.
Yeah, you know, a big part of starting on this was developing consensus. Is memory safety we all agree is a priority, and if so, when we all agree it's a priority, are we saying the same? Are we meaning the same thing when we say the same word, memory safety, right? And it has to start there, right? That's a social thing, not a technical thing. I'm fortunate that I think we have a strong consensus, both about what we mean and that we want it. We're investing in it. And I think, you know, if you're working in a project where some people are maybe not sure, I don't think that's immutable. I think that can be a conversation, right? And it doesn't need to be absolutist, right? Memory safety can start now. It can be incrementally deployed. You can find the common ground you have and maybe start from there. Like, what about this kind of bug? This class of bug? Would we benefit from ruling this out, right? And you can also show, right? In the beginning, converting like a parser from like cursors to span, it's a slightly new way to program. It looks a little different, and you need to develop some idioms for how you want to move your span like a cursor. But once somebody's done it the first time, it's so much easier to say, oh, okay, like that's how that should look, right?
Oh, I almost favor what you're saying, and it just does out of my experiences that like people would say, oh, you're too using this more in C++. I'm tired, you know. I'm too old to that, you know, to learn this. Yeah. And in our cases, at some point we were just like, okay, we take your library and move it to a separate repository. You have your own nodes. Use that.
Sometimes it's like that. It do be like that sometimes, but you know, it could be the start of a conversation. You know, what kind of bugs do you want to roll out? You know?
So do you do all these at the same time, or is this like 3 separate years of evolution?
Oh no, we did it all at the same time. Yeah, including building a lot of the analysis. Now, I gotta say, everything I've said until now is something that I think applies to a lot of projects. The fact that we were able to do this all in 1 year, including building the analyses, that pertains to 2 specific people I work with. Sorry, there are only 2 of them. So, but I do think that generally speaking, the adoption part of it, once there's an idiom, that's been done by everyone, like 50, 75 different developers, and they're all doing great with it. And I think that's part of why it moved so quickly. It was just monkey see, monkey do. Everybody wanted it. You know, you're building your patch. It's not done building. You're waiting. Or you're waiting for your patch to be reviewed. Oh, I might as well add some balance checks while we're here. You know, like suddenly you have 2 patches at in the same time it would have taken you to post 1. You know, and nobody wants to miss out if the cool kids are adding balance checks. So then they start adding balance checks. You know. And it's just the new zeitgeist. Yeah, all concurrently 1 year. Yeah. Go forth, add the checks, add the integration to memory safe languages. You'll be fine. You'll be fine.